Have you ever wondered what the universe is truly made of? Today, we're going to talk about a concept that might give us some answers: quantum field theory. This theoretical framework is like a set of blueprints for understanding the universe at its most microscopic levels. Quantum field theory, or QFT, is the result of a powerful partnership between quantum mechanics and special relativity. These two theories, when combined, provide us with the tools to explain the behavior of subatomic particles. These particles, smaller than an atom, are the building blocks of all matter that we know of. QFT allows us to understand how these tiny particles interact with each other, how they form the elements that make up our world, and even how they shape the universe itself. It's a fascinating subject, full of complexities and mysteries that we're still trying to unravel. So let's dive into the enigmatic world of quantum field theory. Imagine if you could be in two places at the same time. Sounds impossible, right? But in the quantum world, it's a reality. Welcome to the mind-bending realm of quantum mechanics, the science of the incredibly small, where the rules of the game are drastically different from the world we're familiar with. At its core, quantum mechanics deals with the behavior of particles at the atomic and subatomic levels. One of the key principles is wave-particle duality. This is the idea that particles such as electrons and photons can exhibit characteristics of both particles and waves. So instead of a particle being in one place at a time, it can be in a state of superposition, where it exists in multiple places simultaneously like a wave. You might be wondering how this is possible. Well, that's where things get even weirder. The moment we try to measure a particle in superposition, it collapses into a single state. The very act of observing influences the outcome, a phenomenon known as the observer effect. Next, we have the concept of entanglement. In the quantum world, two particles can become entangled, meaning their states are directly connected no matter the distance between them. Change the state of one particle and the other changes instantaneously. This defies our everyday understanding of reality, and even Einstein had trouble accepting it, famously calling it spooky action at a distance. These principles of quantum mechanics, as bizarre as they may seem, have been confirmed through countless experiments. They defy our everyday understanding of reality, challenging our perceptions and demanding a new way to view the world around us. Quantum mechanics is not just about tiny particles, it's about the fundamental nature of reality itself. It's about understanding the building blocks of the universe and the strange, fascinating laws that govern them. It's about pushing the boundaries of human knowledge and venturing into the unknown. Quantum mechanics gives us a glimpse into the strange and fascinating world of the very small, setting the stage for quantum field theory. We're just getting started, so buckle up and prepare for a journey into the heart of the quantum universe. Now picture the universe not as a collection of particles, but as a sea of fields. This is the fundamental premise of quantum field theory, or QFT for short. So what exactly are these fields? In the simplest terms, you can think of a field as a region of space that has a certain value at each point. This value can be anything, from temperature in a room to the gravitational pull around a planet. In quantum field theory, each type of particle, such as electrons, quarks, or photons, is associated with its own field, and these fields exist everywhere, pervading all of space and time. Now here's where things start to get really interesting. Particles, as we know them, are actually just excitations or ripples in their corresponding fields. Think of dropping a pebble into a pond. The pebble disrupts the calm surface, creating ripples that spread out from the point of impact. In a similar way, when energy is added to a field, it creates a ripple, a particle. But fields don't just sit there creating particles. They're also responsible for the interactions between particles. You see, when two particles come into proximity, their respective fields interact, leading to a change in the particle's motion or state. This is how forces are mediated in quantum field theory. For instance, the electromagnetic force between two charged particles is the result of their electric fields interacting with each other. The beauty of this idea is that it unifies particles and forces into a single framework, painting a picture of the universe that is both elegant and profoundly different from our everyday experiences. In the grand cosmic ballet, particles are not independent dancers, whirling around in the void. Instead, they're like waves on a vast interconnected sea, their movements choreographed by the underlying fields. In quantum field theory, particles are merely the ripples on the vast sea of fields that permeate the universe. So next time you look up at the night sky, remember, you're not just seeing stars and galaxies, you're seeing the dance of quantum fields. Ever thought about how particles interact with each other? It's like a cosmic dance guided by the rules of quantum field theory. To understand this dance, imagine a bustling city. Each person is a particle, and the city is the quantum field. Just like people in a city interact with each other, particles too interact within the quantum field. But how exactly does this interaction happen? Let's dive in. In the quantum world, particles are not just isolated entities, they are excitations on their corresponding fields. Imagine these fields as a serene lake. When a stone is thrown into it, ripples form. These ripples represent particles. Now when these particles, or ripples, meet, they interact. This interaction can lead to two outcomes. Either they bounce off each other, altering their paths, or they merge to form a new ripple or particle. This is how particles are created and annihilated in the quantum world. But wait, there's more to this cosmic dance. It's not just the particles or fields that are important. It's also about the force-carrying particles, like photons and gluons. They are the choreographers of this dance. Photons, the particles of light, mediate electromagnetic interactions between charged particles. On the other hand, gluons, the carriers of the strong nuclear force, keep quarks bound together within protons and neutrons. They are like our city's traffic lights and signs, guiding the movement and interaction of particles. So, this is how particles interact in the quantum realm. They dance to the tune of quantum field theory, creating and annihilating each other, guided by force-carrying particles. It's a fascinating dance, with every particle playing a critical part, every interaction leading to a new possibility. Remember, these aren't just dry, abstract concepts. These interactions are happening right now, inside you, around you, and across the universe. In the quantum realm, particles engage in a complex dance of creation and destruction, all governed by quantum field theory. So, what does all this mean for our understanding of the universe? Well, quantum field theory, or QFT, has profoundly reshaped how we perceive the cosmos. It has woven an intricate tapestry that depicts the universe not as a collection of separate, isolated particles, but as a vast, interconnected network of fluctuating energy fields. In the realm of particle physics, QFT has played a pivotal role. It has enabled us to decode the behavior of fundamental particles, from quarks to leptons. It's like having a backstage pass to the grand theater of the universe, allowing us a glimpse into the drama of particle interactions that underpin everything around us. But QFT's influence doesn't stop there. It also has significant implications for cosmology, the study of the universe's origin and evolution. By applying QFT to the earliest moments of the universe, scientists have been able to offer insights into the Big Bang and the subsequent cosmic inflation. In other words, QFT has helped us chart the universe's biography, from its fiery birth to its current expansive state. Beyond the theoretical realm, QFT has also fueled technological advancements. The theory underlies the operation of lasers, those devices that have revolutionized everything from medicine to manufacturing. It also forms the basis for understanding superconductors, materials that conduct electricity without resistance. These applications of QFT have not only deepened our understanding of the universe but also tangibly enriched our daily lives. In essence, QFT has served as a powerful lens, bringing into focus a universe that is both bizarrely alien and intimately familiar. It has shown us a cosmos where particles can be in multiple places at once, where matter can pop in and out of existence, and where time and space are fluid rather than fixed. Quantum field theory, by revealing the fundamental nature of the universe, has truly changed the way we see the world. Quantum field theory might sound complex, and it is, but it's also incredibly fascinating. We've embarked on quite a journey today, delving into the enigma of quantum fields, taking a quantum leap into the deep end of physics, and exploring the fields of reality that underpin our universe. We've seen how particles dance in an intricate ballet, guided by the unseen hands of quantum fields. This theory is more than just academic exercise, it's a key that unlocks our understanding of the universe. It's the language that describes how particles interact, transform, and influence each other. It's a testament to the power of human curiosity and intellect, a reflection of our quest to decipher the cosmic code. So next time you look up at the stars, remember that you're gazing at a universe of fields, dancing to the rhythm of quantum field theory. It's a symphony of nature, a cosmic dance, and we're all part of this grand performance.